Today we're going to talk about uniform circular motion. And you'll recall we were talking before that there was three different things that forces could do to change the motion. If the force and velocity were in the same direction, then of course we're going to speed up the motion. But if force and velocity are in the opposite direction, of course we're going to slow down that motion. The third possibility, and what we want to talk about today, is the case where the force and the velocity are perpendicular to one another. And you'll recall that that results in a turning motion. So what that means, what that is to say, is that for any pure turning motion, and when I say pure, I mean it can't be speeding up or slowing down, it's got to be going at a constant speed the whole time. There must be real forces that produce a resultant force that is perpendicular to the velocity of the object. So let's see how that works out. I've got four cases here. Earth revolving about the sun, clothes spinning in a washing machine, a car turning a corner, and a racing car rounding a bank curve. What I'd like you to do is identify the real forces that produce a resultant force which is perpendicular to the velocity for each case. So pause the video, try the questions, come back for the answers. Case 1, Earth revolving about the sun. Of course, this is going to have to be a field force because there's no contact between the Earth and the sun, and that field force is the force of gravity. And that would be always directly towards the sun. The velocity is, of course, perpendicular to that force, and it's always perpendicular to that force. Now in the case of the clothes in the washing machine, there's a contact force on those clothes, and that's exerted by the drum, the wall of the drum. And that force on the clothes, or in this case on Beavis and Butthead, would be directed as a normal force from the wall of the drum towards the center of the circle. So this would be a contact force, or normal force from the wall of the drum. Of course, the motion is perpendicular to that. That is to say that the velocity is always perpendicular to the resultant force. In this case, the resultant force is equal to the normal force. For the case of the car going around a curve, often I'll get students talk about, say, the force on the steering wheel or something like that, the forces on the axis turning. But we've got to remember, those are internal forces. And we don't want to talk about internal forces. We need to talk about external forces on the car. So we might begin with gravity. Gravity would point straight down, force of gravity. But that's going to be balanced out by the normal force upwards. And so we end up with no net vertical force. And of course our car doesn't lift off the ground or dig into the ground. It doesn't have any interesting vertical motions. We might think about the tires turning around and pushing back on the pavement, and then there'd be a reaction force of the pavement on the car driving it forward like so. That would be the pavement on car. But if it's going at constant velocity, that's going to be balanced out mostly by air friction. But you want to notice here, we've turned the steering wheel so that the tires are at a slight angle. And what that causes is a force from the pavement onto the tires in this direction. So that would be a frictional force, and that's pavement on tires. And that's an unbalanced external force. That's the one that makes it turn around in a circle. And of course that force, that net force on the car, is perpendicular to the velocity. Now let's look at the racing car. This one's a little more complicated because we have several real forces adding up to give this resultant force towards the center. Now if I just start listing all the forces acting on the car, well, there would be a force from the pavement onto the tires pushing the car forward, but that's going to be balanced off by a force of friction that's going to push backwards on the car, and that's why the car is going to go with constant speed. So we're not really interested in those forces. We are interested in the force of gravity. These forces in the vertical plane. So there's the force of gravity. There would be normal forces on each tire perpendicular to the surface. I'm going to represent them as one single force. So this one single force represents the two normal forces on each tire. Now the next force is a little bit tricky because it could act up the ramp or down the ramp. If the car is going really, really fast, friction is going to act down the ramp on the tires, keeping the car from flying off the top of the embankment. However, if the car is going really slow, the tendency will be for the car to slide down the ramp, and friction opposes that motion and pushes up the ramp, holding the car on the embankment. So let's suppose our car is going really fast. So that would mean we would get a force acting straight down the embankment, something like that. That's keeping the car from flying off the top of the embankment. Now to get the resultant force, I need to add those three forces, which means I need to join those three force vectors head to tail to find out the resultant vector. So I'm going to take this friction vector here and join its tail to the head of the normal vector. So there's my friction vector. Next step, I'm going to take the weight vector, the gravitational force vector, and connect its tail to the head of the friction vector. So it's coming straight down like so. Now if I've done that correctly, then if I go from my first tail to my last head, my resultant vector here should lie along the horizontal. So it's pointing towards the center of the circle that our racing car is executing. So this here, our resultant force, is going to be always perpendicular to the velocity of the racing car. Now if we're going to discuss turning motions, of course we're going to start with the simplest turning motion. It's called uniform circular motion. And it just means that there's going to be no speeding up or slowing down, which means that that resultant force is always perpendicular to the velocity. There's never a component of the resultant force that acts along the velocity, because that would cause it to speed up or slow down. And what you end up with is a motion with a constant radius, a constant speed, and a force, a net force, that's always perpendicular to that motion. So this resultant force, or sometimes we call it the net force, or we might call it the sum of all the real forces. It often gets a different name when we're talking about uniform circular motion. When we're talking about turning motion, we often call it the centripetal force. But keep in mind, when we say centripetal force, we're referring to a resultant force for a case where we've got circular motion. So summarizing, we just said that the net force in uniform circular motion points towards the center of the circle. So what direction does the acceleration point? Well, that's very easy, because not so long ago we learned this thing called Newton's second law. And that said, among other things, that the direction of the acceleration and the direction of the net force had to be the same. So the direction of the acceleration in uniform circular motion has to be also towards the center of the circle. And in general, when you think about acceleration, you're pretty much thinking about net force, because the two quantities are proportional to each other and in the same direction. They're almost the same thing. They just differ by a proportionality constant, and their units are a little different. Now some of you might be kind of objecting to all this towards the center stuff, because you've sat on a merry-go-round before and you were thrown to the outside of the merry-go-round. You really had to hold on to keep from flying off to the outside. So it seems like there's a outward force when there's circular motion. So let's try to explain this outward force. And we're going to go back to an example that I think you already understand. Let's say we've got a bus. big yellow bus, and you're standing on that bus, and the bus driver suddenly comes to a stop. So the acceleration is going to be back towards the left. Now, if that's the case, because of your inertia, you'll feel thrown to the front. That doesn't mean that there's a forward force. That's just your inertia. And so the direction you feel thrown in is opposite the acceleration. The bus accelerates to the left, you feel thrown to the right. But this isn't a force, we recognize that as inertia. Now let's take a look at what happens in a turning bus. So let's imagine this is the bus seat, and there's your head right there. A few instants later, the bus, because it's turning, might be approximately here. And here's your seat. And assuming you've got your seat belt on and you don't slide, your head's going to be approximately here. Now, if you were allowed to slide, you would have continued to go in a straight line. You would have gone up like that. But because the seat is holding you in, your head ends up over here. So there's been a force towards the center of the circle exerted by the seat belt and the seat onto you. And so your acceleration is in this direction. But once again, you're going to feel thrown this way against the acceleration. Now this sense of being thrown is really just your inertia. You felt thrown forwards here because of your inertia. You feel thrown outwards here because of inertia. So because of inertia, you feel thrown to the outside. And the direction you feel thrown is opposite to the direction of the acceleration. This animation from the physics classroom illustrates this well. We've got a platform and a ball, and they're moving together in a straight line. But then some sort of force occurs on the platform, causes it to turn. Since there's no friction between the platform and the ball just continues and moves in a straight line. And that's because of its inertia. However, if you're looking from the viewpoint of the platform, you'll notice that the ball seems to slide off the outside of the platform. So from the viewpoint of the platform, there seems to be some sort of force on the ball. However, if we're more objective and we step outside of that accelerating reference frame, then it's clear that there's simply no external force on the ball, so it continues to move in a straight line because of its inertia. So if we want to prevent the ball from going in a straight line, we've got to exert some sort of force on it. And that's what the brown wall is doing here. It's exerting a force on the green ball, causing it to move in a circle with the platform. So let's summarize the difference between this real inwards force and this outwards force that's due to your inertia. So what we call the net force, or the resultant force, or sometimes the sum of the real forces, that's just another way of saying the centripetal force for some sort of turning motion. So this is all about real forces due to contact or fields. And it's always towards the center. And we want to contrast this with what we call the centrifugal force. The centrifugal force is said to be fictitious, as in not real, because it's only due to your inertia. And inertia is not a force. It's something that's apparent in a rotating or accelerating reference frame. But if you step out of that frame, it's clear that it's not a real force. We might even describe it as the lurch, because it's the same as when you're in a bus and you lurch forward when the bus brakes. This lurch is always opposite to the direction of the acceleration. So if the bus accelerates forward quickly, you will lurch to the back of the bus. So if we want to do any sort of mathematical analysis, do we want to use the centripetal force or the centrifugal force? Well, it's got to be the centripetal force, because the centripetal force is real. We don't want to do our analysis on something that's fictitious. So once we're done this video, we'll probably never talk about centrifugal force again, because we don't use it for analysis. Okay, a couple of IB questions. Pause the video, try the question, come back for the answer. First question, the direction of the net force is going to be A. The net force is the centripetal force, and that's always towards the center of the circle. Another IB question. Pause the video, try the question, come back for the answer. So the key idea here is that we've got to have real forces, and they've got to have a vector sum that points towards the center of the circle. So the center of the circle for this plane is going to be horizontal to the left. So if I look at case B here, and I add up these two vectors, join them head to tail, I'd get a resultant that points in that diagonal direction. Well, that's not horizontal to the left. That's not towards the center of the circle. That's not a good choice. The other ones, though, when you add them up as vectors, the resultant does point horizontally to the left towards the center of the circle. But we can eliminate these two here for the same reason, because they're including this horizontal vector to the left. And that's not a real force. The resultant force points in that direction, but the real force doesn't. The real force is caused because of the pressure of the air on the wings, and that real force is going to be normal to the wings. So this is proper here. That's a proper force caused by something real, the air on the wings. So the correct answer here is D. We've used a bit of physical reasoning to explain why the acceleration has to point towards the center of the circle in uniform circular motion. But if we go back to our definition of acceleration, that is, acceleration is equal to the rate of change of velocity, then we'll see once again that that acceleration has to point towards the center of the circle. So a change in any quantity is just the final value minus the initial value. So we're looking for an instantaneous value of this quantity here. Now time here, of course, is a scalar. It has no directional part to it, which means that the acceleration, the direction of the acceleration has to be the same as the direction of this VF minus VI. So if I draw a little circle here, two times that are quite close together, and I consider an initial velocity vector and a final velocity vector, then my acceleration, the direction of my acceleration, should be in the same direction as VF minus VI, that vector subtraction. Or I could write that as VF plus the vector negative VI. And of course the vector negative VI just points in the opposite direction as VI. So I'm taking that vector VF and I'm adding it not to VI but to negative VI. This vector here is negative VI. And if I add those up, the resultant vector, of course, goes from that first tail to that last head. This is the change in velocity vector. And you can see that that direction is towards the center of the circle. Of course, another way to subtract vectors is to place them tail to tail. So if I take my VI vector and place it tail to tail with VF, then the change in the velocity vector is going to point from the head of VI to the head of VF. So once again, you can see that that change in velocity vector points towards the center of the circle. Let's see if you followed that reasoning. Pause the video, try this question, come back for the answer. Well, a quick way to do this question is to realize that if our particle goes from here to here in this direction, then towards the center of the circle would be in this direction. So we're looking for a delta V in that direction. This one's not right. This one's not right. That looks good. That's in exactly the wrong direction. So the correct answer here has to be C. So what we can see here is that VF is joined to VI, tail to tail, and the subtraction of the two vectors goes from the initial velocity to that final velocity in this direction. Now, if I've got an object in uniform circular motion, I can entirely specify that motion by the radius of the circle and the speed that the object's traveling at. So I should be able to write the acceleration entirely in terms of that speed and that radius, and that's what I'd like to do now. Now, just using a little bit of physical reasoning, I would say that the acceleration should vary inversely with the radius. If I've got a really big radius, then the velocity isn't changing very quickly because it's not changing its direction very quickly. It's almost going in a straight line. So a bigger radius for the same speed should mean a smaller acceleration. And similarly, I'd argue that if you have a bigger speed, you're going to get a bigger acceleration. Because if you're going at a higher speed, you're changing your direction more quickly, and you must be accelerating more quickly. So as a first guess, I might say the acceleration should equal speed over radius. Now it turns out, and I'm not going to prove it here, it turns out this speed is actually more important. It gets squared. And this here is our formula for centripetal acceleration. So if you tell me the radius of a circle and you tell me how fast an object is moving on that circle, I can tell you how big the acceleration is. Now I can take this a little bit farther because I know by Newton too that the net force must be equal to the mass times the acceleration. And if we have uniform circular motion, that net force, we call it the centripetal force. And it would be equal to the mass of the object times the acceleration, which we know is v squared over r. So we've kind of got two equations for the price of one here. One for centripetal force, one for centripetal acceleration. But of course the acceleration and the force in the same direction and proportional to one another. One final question for you. What I'd like you to do is pause the video, read the question over, try it out for yourself, and then come back for the answer. So we have uniform circular motion. We know that the centripetal acceleration should be equal to v squared over r, and in this case we've got a speed of 20. That is SI units, so I don't have to change that. The radius is 50 meters, so I end up with 400 divided by 50, that is 8 meters per second every second towards the center for the acceleration. Part B, the net force. Well, that's easy because I just take my mass and multiply it by my centripetal acceleration. So that's going to be 1,000 kilograms times 8 meters per second squared, or 8,000 newtons would be the force of friction acting on that car. Part C, what exerts this force? We talked about this earlier. It's the pavement on the tires. And part D, why do passengers feel as if they are being thrown to the outside of the car if the force is inwards? Well, that's simply their inertia. It's not a real force, it's a fictitious force, an apparent force when you're in a rotating frame. So let's summarize those big ideas from the video. So when we have uniform circular motion, we always have a net force and acceleration towards the center of the circle. And this net force is given the name centripetal force. And it has to be related to to the speed and the radius of that circular motion. And that centripetal force will be given by the mass of the object times the speed squared over the radius of that circular motion. Keep in mind that that so-called outward force is just inertia. And because it's not a force, we don't consider it for analysis. We always look at what's real when we want to do analysis. And that's all for today, folks. Thank you very much.